Induced currents by magnetic fields can be quite tricky, so let's do a quantitative example of this using Faraday's law. So we have a loop of current, which has a 10 centimeter diameter, and a resistance of 0.1 ohms. It's really small resistance because it's just a loop of wire. And it's placed in a magnetic field that is increasing from 0 to Tesla to 2 Tesla in 4 seconds. And the magnetic field is supposed to be uniform throughout the region that the loop is in. We want to know what the direction and the magnitude is of the induced current. So the first thing we need to do is figure out the direction of the induced current. And to do that, we need to think about what the flux is doing. So the flux is increasing out of the page. So there is going to want to be an induced magnetic field into the page in the region inside the loop. The only way to do that is if the current goes clockwise. And note that we're using the idea of Lenz's law to figure out the direction of the induced current, because the induced current is going to want to create a magnetic field that resists the change in flux. Now that we've figured out the direction of the induced current, let's find the magnitude of the induced current. And so we're going to have to calculate the amount of flux inside of the loop. And the flux is the area of the loop times the magnetic field inside the loop. So the change in the flux is the area times the change in the magnetic field. The area of the loop isn't changing. Now Faraday's law tells us that the EMF induced in the loop is the change in the flux over the change in the time, and we're just going to take the magnitude because we've already figured out the direction. And the change in the flux per change in time is really the area times the change in the magnetic field in the change in time. And plugging in our numbers, we get a result for the EMF that's induced in the loop of 3.9 times 10 to the minus 3 volts. Now that sounds like a really small EMF, but it's also a really small resistance inside the loop. Now how do we figure out the current? Well, we need to go back to what we learned before about currents and use Ohm's law. The EMF acts like a battery, acts like a voltage source, and so the EMF is equal to I, the current, times the resistance. Or rearranging, the current is the EMF divided by the resistance. And plugging in our numbers, we get 3.9 times 10 to the minus 2 amps for the magnitude of the current. And again, that current was going in the clockwise direction.